I'm just going to quickly go through some ways for writing formulae for things that you're going to encounter in this topic. So it will be old news for most of you. The two main things we're looking at in level 2 are either ionic compounds or molecules, particularly in this topic. So those molecules might be elements where they're only made up of one type of atom, or they might be compounds where they're made up of more than one, like the example given there. Start with ionic compounds though, because they will always be made up of a cation and an anion. So the first thing I really want to go through is the order you have to put them in. This is a convention, which means you have to do it. We always write the cation first and then the anion. And if you write them out with their charges, it makes the next step quite easy. So I'll put the for magnesium carbonate, I'll put the magnesium ion there and the carbonate ion there. The thing I'm looking for is to get their net charge to be 0. So 2 pluses and 2 minuses, for every 1 magnesium ion in the crystal or in the solution, there has to be 1 carbonate. So we write this ratio of MgCO3. Yeah, it means 1 magnesium atom, 1 carbon, and 3 oxygens. But what's more important is that it's 1 of each ion in a 1-to-1 ratio. It's going to be billions of each, more than that in fact, in a solution or in a crystal. But they're in a 1-to-1 ratio. So that's what that formula means, in a 1-to-1 ratio. So this is only a ratio. What happens if I have things that are not the same charge? And I've given an example there of ammonium sulfate, where ammonium only has a 1 plus charge, but sulfate has 2 minus. So to balance that out, there has to be a 2-to-1 ratio. So there's 2 positives for every 2 negative. And so I've got a 2-to-1. You might have heard the little thing drop and swap. What I've done is I've taken the 2 from there, dropped it, and then swapped it onto the other ion to be a subscript, which we can see there. It's not the reason for this being the formula. You can't say it's the reason, but it's a quick way to work it out if you're having to balance equations, which we're going to do later today. So when I write this, I have NH4 2SO4. Well, if I didn't have the brackets there to show that that's 2 of this whole thing, then it would say NH42, which would be 1 nitrogen, 42 hydrogens, and so on, which is wrong. I need to say that it's 2 of everything inside there. 2 nitrogens, which we've got there, and 2 times 4 is 8 hydrogens. That's what we've got here. So we write it like that. You'll also notice in both of these the charges have been removed. Even though they're still ions, they're not atoms, they're still ions, we remove that charge because we're showing the formula for the compound, the ratio in which those ions exist. But we're implying, actually more than implying, we're stating that this is neutral. There is no net charge because for every 1 positive charge there is 1 negative charge to cancel it out. If there were a charge involved here, it wouldn't be a compound, it would just be an ion. And it could be a complex ion, which we'll get to later in the unit. So they do exist, things that look like molecules but they have a charge, are called a complex ion. But we're trying to, with ionic compounds, have no net charge. Okay, so cation then anion, for naming it and for writing the formula. Charges are dropped, charges cancel out. So we've got a net charge of 0. That's your ionic compounds. Molecules are a little bit different insofar as their names are really easy for giving away what their formula is. So the one I've given there is carbon dioxide. So you just need to know that mon or mono, di, tri, and tetra, or it can be tetro or tetra, depending on if the next one's a vowel. So like for iodine or oxygen, you wouldn't put the A in there. It would be tetroxide or tetraiodide. What those names mean, 1, 2, 3, and 4. Beyond that, it's the names of the shapes. So pentagons are 5-sided shapes, so it's penta something, and so on. The weird ones you might not know, hept, H-E-P-T for 7. You shouldn't get that high, to be honest. Okay, so they are the main ones you're going to meet. So carbon dioxide. Now over here, the formula was a ratio. This is not a ratio. This says that every single molecule is made up of a single carbon bound to 2 oxygens, covalently bound to 2 oxygens. and they travel around as molecules with their own electron cloud and with interactions with neighbouring molecules, whether they're more carbon dioxide or other things. So they exist as a molecule. It's not giving us a ratio. It is 1 carbon and 2 oxygens for every single CO2 particle. Now if it were dry ice, then we're getting into, okay, it's got billions of carbons and twice as many oxygens. So it's a bit like a ratio. However, they all exist as discrete or individual molecules with bonding in between them, called, not surprisingly, intermolecular bonds. And again, we'll cover that more in a future topic. Okay, so rather than a ratio, these are what we call discrete molecules. And in this topic, you're going to come across ionic things that might react to give off, for example, carbon dioxide or oxygen gas or something like that. And so you need to be able to write ionic formulae and molecular formulae within the same balanced equations. Some common examples you might have met before. So where you react carbonate, which is an ionic compound, so sodium carbonate, for example, with an acid, which is either going to be molecular or ionic, depending on which acid it is. When they react, they give off CO2, which is definitely a molecule. But they also make an ionic salt, so an ionic solution to go with it. So you need to be able to work with ionic and molecular formulae in the same equation. Alright, so you need to know what those are. Any questions before I turn this off?